So welcome everybody. We are welcoming today María del Rosario Martínez-Ordaz, who is a researcher in philosophy at the Federal University of Rio de Janeiro in Brazil, and also a visiting scholar at the Nicolaus Copernicus University in Poland. So she received her PhD in philosophy of science from the National Autonomous University of Mexico in 2019, and she works in general philosophy of science and philosophical logic. So today she's gonna discuss how we can have scientific understanding when we are ignoring the theoretical structure, and illustrate this case with neutrinos that are a very contemporary topic for fundamental physics. So I foresee this will be very interesting. The topic of being able to progress in science while we don't know the underlying theoretical structure is basically a lot of our everyday life, I would say. So I think this will have a lot of connections with the work of the physicists, and but also some very good philosophical insight. So with this, Maria, I give it to you.
Thank you very much for the introduction, and thank you very much for having me. Just a second, I'm going to start sharing the screen. And just another second so I can come back for you to see me. Yes, so thank you again. Thank you very much for having me. And some disclaimers, or maybe the main disclaimer is that I am a philosopher of science, but I am not a philosopher of physics. So I have been working from general philosophy of science combined with epistemological worries and some formal tools from logic in order to address some bits of the rationality of scientists, especially in empirical sciences. But I always find case studies from physics more interesting or more revealing or more clear to study than other disciplines, or at least I think that. So the question that today I'm going to be addressing is how do physicists overcome high degrees of ignorance in order to gain deeper understanding of the object of the study. The aim of this talk is going to provide you with a sketch of an epistemological landscape of the detection and overcoming of high degrees of ignorance in order to gain knowledge and understanding. The main thesis that I will be defending here can be summarized by the following two observations. First, the ignorance associated with the heavy technological implementation in physics especially is of one particular type, ignorance of theoretical structure. And second, the partial overcoming of this type of ignorance is associated with the production of specific insights that later on will lead to further epistemic achievements such as knowledge and understanding. So with that in mind, the talk is going to be divided in four main parts. The first one is going to be a little bit the longest, which is going to be the preliminaries, a bit of language and discussions from the philosophy of science about anomalies, ignorance, etc. The second part is going to be focusing on a particular case study of the measuring of the solar neutrinos flux and what was called the solar neutrino problem. I'm going to pay more attention to the Macau and Davis experiment, but then I'm going to say generalities about how the problem was partially solved in the long run. Then I'm going to talk about how to overcome ignorance of theoretical structure in order to go to these other epistemic goods, such as understanding, and then some final remarks. So first of all, this is a word that many of you have listened, have heard in the development of your academic life, which is anomaly. So imagine the following. I have a theory that predicts that a planet is going to be in a particular place, and then I look for the planet and the planet is not there. So we call that an anomaly. If I have an explanation of why I don't see the planet over there, and I add some auxiliary hypotheses in order to get this explanation, then the anomaly gets dissolved. So anomalies are not only the problem that emerges, but also the word anomaly is related to how long it lasts. If it's just a misunderstanding between two communities, then it it looks like an anomaly at the beginning, but it's only apparent. Then you get a solution for it and it's solved and it's not a problem anymore. Also, if you get an explanation of why your theory is not accounting for that phenomenon, then the anomalous part of the discovery gets dissolved, or at least weakened. So in philosophy of science, we have studied anomalies for almost a century, but one of the main characterizations of what an anomaly is comes from Lacatus in the 70s. Lacatus said that anomalies consist of the presence of a statement, generally some kind of observational outcome or prediction, that we can say it's S, such that when combined with a particular theory, G, and with a ceteris paribus clause, the statement becomes a potential falsifying statement for the theory. And this is the part that becomes really problematic for scientists when they discover an anomaly, that maybe the anomaly is telling them that the theory is mistaken. In that sense, anomalies get attention not only from the scientists, but also from the philosophers, because the study of the reactions of the scientists towards anomalies is going to tell us a lot about scientific rationality. In the way in which we handle or we detect and we explain out these type of problems, tell us how rational scientists are when working with information that they consider to be unreliable, defective, or even worse, refute potential falsifiers for the theories. So what has happened after Lacatus' characterization of anomalies is that philosophers claim that it was too broad in order for us to use it in analyzing scientific rationality. So we came up with two definitions of distinctions between anomalies. On the one hand, we have something that we associate to gaps, explanatory or predictive gaps, and we call them lacunes. So this term comes from Theo Kuipers, was also present in Larry Loudon's literature, but the terminology is coming from Kuipers. And that means that either explanatory or predictive gaps are present in the following form. I have a theory that neither predicts nor forbids the presence of S. And I have an experiment that does not forbid the presence of S. And so I detect something that looks like the negation of S, for instance, and that it's novel with respect to the theory, because the theory didn't say anything about this phenomenon. Think about the anomaly in the perihelion of Mercury. At the beginning, it looked like this. At the beginning, it looked like the theory didn't tell us something about why Mercury was going to be moving that way. But the good thing about lacunes is that they are hints of what we have to search. So in the case of the anomaly in the perihelion of Mercury, what we had to search first was a planet that was located between Mercury and the Sun. So it was an easy task. We just had to locate that planet. When we didn't locate them, when we didn't find the planet, then we had to move to another hypothesis. Maybe there were some asteroids in between, so just look for them. When we didn't find them, then the problem wasn't that clear that it was one of these types of anomalies. Nonetheless, at the beginning, we had the impression that it was just a matter of gathering more data, or we didn't have enough information about which is the status of the planets outside. We are missing one bit of a planet in between Mercury and the Sun. So lacunes are often related to ignorance in an explicit way. We often think of them as good discoveries because they are going to allow us to find more information in order to get more robust either our theories, our models, our explanations, and so on. So these are really good things when we find them in our scientific practice. In contrast, there are other types of anomalies which are more associated to the refuting character that Lacatus had in mind, which are things that we can associate to logical contradictions. And in this case, a contradiction between a theory and a prediction, an observation.
Excuse me, Maria, we are still seeing slide 6. Is it expected?
Oh. No.
Okay, now I'm seeing slide 7.
So, okay, good. I'm going to start moving here then, because maybe when I share it, it doesn't move. So I'm going to move from here. But
Okay.
When we have logical contradictions, what happens is that a theory is predicting certain things to happen, like S, but an experiment is giving us something different, radically different, that we can interpret as the negation of S. So in that case, the negation of S, or the absence of S in a very problematic way, it's understood as anomalous, but also as inconsistent with the theory. So anomalies in this sense are often related to error, in the sense of epistemic error. We are not grasping what we are talking about. We made a calculation mistake. We are very much mistaken about the applicability of the theory in this particular domain, and so on and so forth. But they are also related to logical triviality. So if my theory is a formal theory that it's expected to behave classically, and it's entailing contradictions with sets of information that it should be consistent with, then I am in risk of having an explosive theory that will, in the long run, be trivial. So in this sense, logical contradictions are very much the opposite of lacunes. Those are things that we don't want in our scientific practice, because we don't want to work with them. There is no hint of what to fix. Actually, it's a hint of we are doing things badly. So this often give us take us to this point in which we say, okay, so we have anomalies, but they can either be of the form of explanatory or predictive gaps, lacune, or they can be contradictory types. If they are of the former type, then we can easily say that the source of this anomaly is ignorance. And we can even get some hints about how to fix this ignorance. In the case of contradictions, it's not clear where they are coming from. That's the traditional view. So now let's go and see what ignorance is for philosophers. Philosophers traditionally had understood ignorance as lack of knowledge. There are now there is a new account on saying something a bit different, but we are not going to focus on that one. So as lack of knowledge, which is the most intuitive characterization of ignorance, ignorance can be of at least 4 types. First, it can be factual, meaning that we lack knowledge about facts, whether something is the case or is not the case. That also translates in us being unable to determine the truth value of certain propositions. So if I have to choose whether this sentence is true, then if I am factually ignorant, I am also going to be unable to determine whether that sentence is true within a particular model or not. Now, there is other type of ignorance, which is objectual ignorance. And this relates to the fact that sometimes we know people, and we can express that by providing lists of properties of these people in order and an explanation of how all these properties hang together. The same happens with places, with things, with objects, but also with phenomena in general. So objectual knowledge is more than knowing list of facts, but also having explanations of how these facts come together about a particular thing, person, entity, etc. We also can find procedural ignorance, which means that we cannot know how to follow a recipe. We don't know which are the steps that are crucial for going from one place to another, epistemically speaking, and we also don't know which are the ones that are auxiliary but not necessary. So in the case of having procedural ignorance, we can have 2 different presentations of it. On the one hand, we might have ignorance of not knowing the steps explicitly, but we are expected to be able to let others know that we know what goes after what. On the other hand, there is another presentation in which we are not obliged to provide this type of explanation, but we are obliged to perform certain type of task. So a good case of procedural knowledge of this type is when we are able to calm a crying baby. Maybe we cannot explain how we did it, But if we can perform that task successfully in the majority of cases, then it seems that we have knowledge of how this procedure goes, even if we cannot explain it to others. In addition, there is a fourth type of ignorance that is related to the others, which is lack of answers to questions. This means if somebody asks me something, I cannot even start explaining how to respond to that question. That relates to all the other three types of ignorance. Now, let's assume that any of these type of ignorance causes lacune. What causes contradictions? If we look at the literature of how contradictions emerge in science, then we can find something that I call the generic explanation, which goes as follows. First, when having two scientific statements that contradict each other, scientists tend to assume that at least one of them is false. And I think that's a natural intuition. If scientists are able to distinguish which of the conflicting propositions should be regarded as false, they would be able to explain how they could satisfactorily work on seemingly false information. If we take that contradictions are false intuitively, but I can explain how these two things do not contradict with each other because one is an idealization, so I don't take that seriously, that part of the contradiction. But the other thing, I take it to be like a true description of the world, then I am also explaining how these two things are not expressing the same thing or are not talking about the same object in the same way at the same time. So the contradiction is in a sense dissolved. And now I can tell a story of how I am using this falsehood that comes from an idealization, abstraction, fiction, whatever, in a rational way. Even if it looks inconsistency from the outside, I have a consistent explanation of how it is not actually inconsistent. So, however, most of the time, when we are scrutinizing cases that look like inconsistencies, when confronted with an inconsistent set of information, scientists ignore at least which of the mutually inconsistent statements should be regarded as false. Now, once that they recognize this ignorance, if they have no better alternative, meaning no consistent alternative, no clear alternative or set of propositions, the toleration of the contradiction becomes the only option at hand. Such a tolerant attitude towards contradictions is often seen by scientists as a temporary resource. This especially because of the connection with ignorance. So, as I was saying in the case of lacunes, when we find that we have an explanatory gap or a descriptive gap, then we have an idea of what to fix. It's the same in this case. If we assume that contradictions are also caused by ignorance, then we are also searching for more information, the information that we need in order to weaken the conflict or dissolving it. Now, that takes us to this point. So both things are caused by ignorance. Maybe contradictions are more clearly caused by factual ignorance because the starting problem is that we cannot determine the truth value of the two propositions. So we can say that ignorance is present in the emergence of both anomalies. But what causes the factual ignorance in the case of contradictions? Even more importantly, what causes the resilient character of anomalies? Because if you remember correctly, when I start speaking today, I mentioned that anomalies are characteristically long-lasting in science, and that's what makes them more interesting. So my idea is that it is ignorance of theoretical structure. And ignorance of theoretical structure means lacking knowledge of the relevant inference patterns that scientific theories or models allow for. When ignoring the relevant parts of the theoretical structure of a theory, scientists are not capable of grasping abstract causal connections between the propositions of their theory. They can neither identify the logical consequences of the propositions that are working with, nor can explain under which circumstances the truth value of certain propositions will be false, at least will be false. Now, this ignorance of theoretical structure is not only present in general, but particularly in heavy technological implementation scenarios. If one cannot explain how certain heavily mediated observational reports are gathered, one must weaken one's belief of them when being evidence of something being the case. So if I have no clear justification of how this thing was produced, then it's not clear that I have a justification for calling this knowledge. In empirical data-driven science, certain outputs of computational procedures are expected to come as observational evidence, equally as an observational report from an experiment in a laboratory, of something occurring in a particular way. However, when present, ignorance of theoretical structure regarding these, the procedures and the instruments through which these outputs are obtained, messed up with scientists' capability to explain how these outputs have been generated, without necessarily affecting the scientist's capability to explain why a particular phenomenon would occur in a specific way. So this leaves us with the idea that scientists sometimes cannot explain how reliable their products are. Yet, they can relate these products successfully to particular theoretical frameworks. Now, that said, so far we have said the following. We have related ignorance of theoretical structure, saying that it's often causing the other types of ignorance. If we don't know how the bits of the information should hang together within a particular theoretical framework, we are going to end up being unable to determine procedures, to determine the truth values of certain propositions for the case of contradictions, but also unable to determine how certain descriptions of phenomena hang together and providing explanations about that. So anomalies now seem to be related not only to ignorance broadly constructed, but to a particular type, ignorance of theoretical structure. Now, the options that we have are rational rejection, rational acceptance of the problem that we have, or the toleration of either the incompleteness or the inconsistency. So the first option, which is rational rejection, will require us to explain which of the elements is false or why one of these is problematic. But in the case of ignorance, it's clear that we cannot provide this explanation. So it seems that at this point, rational rejection, it's not a real option for us. Rational acceptance now. Rational acceptance would require us to commit to the truth of any of these two scenarios. One in which we say that incompleteness is, for instance, part of the properties of the object that we are studying, or inconsistency is part of the properties of the object that we are scrutinizing. But it doesn't seem that we have justification for that, because initially we said we actually are ignorant of the facts that surround this anomaly, so we cannot determine how to solve it. So we have no justification for rational acceptance either. What means to be inclined to have rational toleration of either the incompleteness or the inconsistency? This is an epistemic phenomenon which will take place once an agent identifies that something is defective, meaning incomplete or inconsistent at least, in a relevant part of the reasoning, their theory, their models, but they are going to still be able to reason with or from this defective information to reach interesting conclusions or novel conclusions. And they also are going to be able to distinguish between differential products of the reasoning that are sensible given a particular context from those that are not. So at this point, we have the following scenario. We can either go from these anomalies to rejection, to acceptance, or to toleration, at least for the motivation of that. But we have already dismissed the options of rejection and acceptance at this point because of ignorance. But what is affected by the resilient character of ignorance of theoretical structure? This is the next question. And the answer is there are certain epistemic goods that are going to be in upper levels, not only knowledge, but particular scientific understanding that are going to be out of reach in cases in which we ignore theoretical structure. Let me tell you why. Scientific understanding has been often characterized as consisting of knowledge about relations of dependence. When one understands something, one can make all kinds of correct inferences about it. It is often regarded as factive, meaning that the content of understanding can only include true propositions. We can only understand whatever we know to be true. And it is often regarded as explanatory, meaning that explanatory knowledge, causal explanatory knowledge in particular, is often seen as a prior condition for the achievement of understanding. So in the cases in which we are really ignorant of the theoretical structure, we are going to find ourselves unable to reach understanding because we cannot see certain connections that are going to be crucial for moving forward in our epistemic route. So the main issue is the following. There are going to be, especially in heavy technological, when there are scenarios in which we have heavy technological implementations, scientific success is also an outcome of these heavy technological implementations. Yet, it comes with a significant increase in the physicists' ignorance regarding the ways in which the data is gathered and processed and hangs together. When we relied on machines in order to tell us something that we wouldn't be able to produce ourselves, then sometimes of epistemic opacity come to the discussion. And these epistemic opacities are mostly related to us ignoring which is the underlying theoretical structure of these technological implementations, of even of our own theories with regard of these technological implementations. Now, ignorance is more common and more accepted than before. When we accept that scientific success in these scenarios comes with the price of having more ignorance, then we are more tolerant towards it. And we are more open about not knowing, for instance, what machine learning does or what deep learning does and big data implementation in general does for the science. Usually the communities of the theoreticians that are working in the field are not overlapping with the communities of the programmers of the machines or the designers of the experiments in the technological sense. And so, and we are fine with that. However, scientific understanding, well, being very important, will require us to get rid of this type of ignorance. It's not clear how it can be achieved in contexts in which high degrees of ignorance are still present, as a matter of fact. And this gives us the impression that there might be certain regions of scientific knowledge that, in spite of being crucial for the achievement of scientific success, might not be candidates for being understood in some significant way. But keep in mind that scientific understanding is one of the top aims, epistemically speaking, of scientific enterprise in general, because it will allow us to connect every bit of knowledge that we have about a particular domain and build a more comprehensive picture of that domain. So this is going to be a serious issue. Now, let's move to the case study. And let me tell you a short story about it. This is going to be about, as I was saying, Macau's and Davis' experiment. But first, some historical remarks. So in the 30s, the first anomaly that they were solving was the beta decay phenomenon. They couldn't explain how being a two-body phenomenon was consistent with what we knew about conservation of energy, right? So Pauli came up with the concept of neutrino. And while neutrino was successfully added to the problem of beta decay in order to explain it out, it came with its own problems. First of all, it was a subatomic particle, a fermion, electrically neutral, either with having a tiny mass or being actually massless. The problematic part is that it interacts only via the weak interaction and gravity. And because of this, it almost never interacts with normal matter. So they actually escape freely from their sources more often than can be detected. And this for Pauli was a pity, because that indicated for him that neutrinos were not measurable or tested. There was a good epistemic backup for claiming that they existed, but it was not clear how they were going to be able to measure them. So there were some challenges for designing an experiment after that, but the scientists and the general communities were convinced that neutrinos actually existed and that they were deserving a test type of experiment. So first, some of the problems associated with how to build this experiment is that neutrinos do not absorb light, don't have an electric charge, and are of extremely light weight. So the only way to study them is by their interaction with weak nuclear force. When a neutrino interacts with an atom, it produces other particles. So we can detect neutrinos by measuring these other particles that are produced. And now the sources, they had two options. So they can either go for the natural sources, which are going to include the sun, cosmic radiation, etc., or the man-made sources, which are going to be particle accelerators nowadays and nuclear power plants. So either we can go for approaching huge numbers of neutrinos or antineutrinos, or having huge detectors in order to catch at least one neutrino every time. So with that in mind, there was first the Rhines and Cohen experiment in 1951, and especially there was the first version of the Poltergeist project, which actually showed that there was, in a sense, a desperation for testing the presence of neutrinos. So the community was really eager to test and measure the neutrinos flux. And so in the 60s, Macau designed, first found out that he wanted to work with in the detection of neutrinos, but there was no theoretical framework in order to predict how many neutrinos were going to be in a reliable way. So the first step for him was to develop what was called the Standard Solar Model, a theoretical framework derived from the application of laws about energy conservation and transport, and all of this you already know, so it doesn't really matter. So that happened in 63. And when he contacted Davis about whether Davis could develop the experiment, they discovered that they met certain resistance from the Brookhaven National Laboratory, because ideally they didn't think that the Standard Solar Model was already refined enough in order to be tested, and that it was going to be a waste of money and a waste of time to develop a new experiment and try to check whether the predictions that the Standard Model was giving at the moment were accurate. Nonetheless, that also inspired the idea of, well, if we are so resilient, maybe that is a good indicator that this is a worth to be pursued task. And so the experiment, I'm not going to dig on the details, but the experiment combined, importantly, a lot of knowledge from radiochemistry, as Davis was working as a chemist, the beginning of neutrino physics, nuclear physics, among other areas of physics, as well as a complex apparatus and instruments, so a lot of engineering to build a super cool underground tank, and the data mining strategies in order to interpret the Geiger counter results. So this was a liquid type of experiment, so it relied on chlorine and on the cross sections between chlorine and argon, and so on. But one of the important tasks was to determine how to interpret the outcome. So not even the clicks from the Geiger counter were reported to be like directly outputs, but they had to be filtered before. So, and in this sense, when we look at the development of this experiment, we can see the beginning of something that we are going to start calling heavy technological implementation in the later literature. So there are a lot of epistemic opacities around this, because there are a lot of groups working together from different backgrounds, not really having a grasp of how technology from one field is going to relate to the technology of the other. So the fact that it was the first type of experiment in this sense also sheds light on the problems that we are going to have right now when growing into the technological implementation realm. Now, the results of the experiment, as all of you know, were really problematic. So in the 67, Davis did the experiment, and the results were that there were like 2.5 or 3 times different, larger than the results that were calculated by Macau. There was a situation in which Davis blamed Macau's calculation and Macau blamed Davis' experiment. So they had to go back and work on the experiment and the refinement of the Standard Solar Model for some months. And then they tested it again, and still the problem was there. Even if the predictions and the observational outputs were narrowed, the problem was still significant. And the problem remained unsolved, as many of you know, until 2001, when it was actually explained. It was not only measured, but explained that neutrinos are of different types and that they have actually mass. And with this, it was clear that they ignored those facts when they started developing the experiment, and also that ignorance originated the anomaly. Now, the question is which type of anomaly we are dealing with. Is it either of a Lacan type, which looks more intuitive, or is it a contradiction? So one of the first things that we are going to notice if we look at the sociology of this experiment is that they didn't know. So if one looks at what happened with Davis from his point of view and his work with his colleagues, one would notice that he didn't think that, first of all, the problem was in his experiment, but also they didn't think of the problem as being an inconsistency. They thought that they only had, were lacking information, or the data mining resources that they had at the moment were not fine enough, and they just had to narrow them, and that was going to be it. So this is a quote from Pinch's book, which is a sociologist's approach to the case study. And he interviewed Davis about the first presentation of his results, which was in August 1967. So the results came out in June, late June, the beginning of July. And then he checked them. He was a bit annoyed because of the difference, but then he decided to just present them in a conference. And his report was, I just gave a regular contributed paper and I gave it to an audience of about 6 or 8 chemists who sat in the room. And I mean, they didn't care less. And this is something that Pinch emphasizes, that it is so weird that a discovery that was going to be groundbreaking for neutrino physics was so overlooked by the chemist. What we can say about this reaction and the further reaction from the chemist community is that the results were quietly acceptable for them. The methodology that underlied the chemical part of this was quite decent and quite accessible for others to evaluate, and it looked nice. So the results seemed to be reliable. It was not something that they start mistrusting at the beginning. And this is just one of the components of something that could be a contradiction, right? You also have even Davis' boss, Goldhaber, saying that he didn't believe that the problem was Davis' result, but was Macau's. And he was the most resilient person around the experiment before getting the funding about actually being the theory of Macau's ready in order to be tested. So all of this the combination of these facts seemed to show that at least this community believed that the problem was of the type of incompleteness. Nonetheless, if we look at Macau's testimony, that's really interesting. So he says that Ray Davis went to Caltech and gave an informal seminar in which he discussed the preliminary results of the experiment. This was already 1967, and it was around after having the first presentation and having all the discussions about where could the problems be coming from. And so Ray Davis said that Richard Feynman was there, look at whatever his reaction was when Davis presented, and then talked to Macau and said that, look, this is not so problematic. It's a good thing that they discovered that the theory doesn't match the experimental results. It's going to make the discipline go further, but it's not your problem. But Macau's reaction and some of the testimonies that he gives in the corresponding interviews actually exhibit that he thought that it was a contradiction, that it was not something that they could be explaining by saying there is a margin of error that can explain this, but that it was a legitimate problem that could be interpreted as having a prediction and the negation of that prediction, both combined, and more importantly, both equally justified. Because as I was saying, if we look at the reaction from the Davis experiment and the communities that it was presented to, then we seem to detect that there was a huge epistemic backup for that. So it was not a result that was unconvincing for the community, but actually it looked very decent. So, and the same happened for Macau's group. They revised the standard solar model over and over again, and it looked very convincing for all of them. So they both had in their hands propositions that were equally justified, but they didn't know how to weaken any of the commitments behind any of those. And so that takes us to the picture that we had before. So we said there is some ignorance of theoretical structure that might be causing the presence of lacunes and contradictions and anomalies in general. And so in this particular case, even if we couldn't decide at the moment whether this was a contradiction or was a lacune, we can trace back the origin of the problem and say they were ignoring something. What was that? And in the long run, we will discover that they were ignoring the elements, the theoretical elements, and the connections that held between them that grounded both the experiment and the standard solar model. The properties of what a neutrino is, the types of neutrino that could be out there, and the relation that would exist between them was something that was part of what they ignored. And so in that sense, we can call that ignorance of bits of the theoretical structure. And again, in this particular case, they didn't have evidence for the rejection or for the acceptance of any of those defects. So they have evidence for having the backup for the prediction and the backup for the observational outcome, but they didn't have anything else to dismiss any of those or to accept both of them as being part of the accurate description of a particular phenomenon. So they were motivated for toleration. Now, if we look at the hypothesis that we are going to find, we are going to see that Bruno Pontarcovo in the 50s.
Maria?
Yes?
If you still have 20 slides, is it possible to go over them a bit faster? Because we still
I am not going through all of them, but okay. Yes, I'm going to go fast now. So in the hypotheses that were historically available, we are going to see the recurrence of neutrino oscillations possibility coming from time to time, but scientists were still not able to accept it for different reasons. But we are also going to see hypotheses that appeal to the fact that the theory is not ready to be tested, or that neutrinos are not well enough defined in order to be detected. So we still weren't ready for testing the theory at the moment. So we are going to see many different hypotheses interacting with each other. Another popular hypothesis at the beginning was that the cross-sections between argon and chlorine were not really clear for the chemists. And so to use these elements in order to reveal something about the presence of neutrinos was a mistake, a methodological mistake, and so on and so forth. And so what we are going to see also in this case is that there is an epistemological explanation that tells us that they couldn't detect which type of anomaly they were handling because they didn't have epistemic clarity about how the pieces of the theory and the model and the experiment relate to one another. And this is something that is often called lack of observational independence. So they had an experiment. Ian Hacking has a discussion on this particular case. They had an experiment which theoretical grounds overlap with the theoretical grounds of the model that they were testing. This gave us a very messy scenario in which the strategies that they could use was not just the problematic parts and leave them aside, but they had to develop a way to get clarity about this theoretical structure that was shared between the model and the experiment. And so, but now take this same case and wonder how can we move from recognizing this type of ignorance that is surrounded all the environment to move to gain some epistemic goods such as knowledge and understanding. And the first step is to ensure the reliability of the information or the method surrounding the anomaly. So this is something that is often indicated by the selection of inferential patterns. So the strategies that we have to handle the defective information and not multiply the defects, neither incompleteness nor inconsistency. And so these strategies can be of different types, but ideally they also allow us to get grasp of the bits of the structure of the theory or the model that we cannot grasp from the outside. So they consist of exploring in a safe way what we have in order to detect which elements actually are needed as part of the theory or as part of the development of the experiment and the reasoning, and dismiss the ones that are maybe less reliable. So once we have this, how can we move to other epistemic goods such as understanding once we have the justification for the tolerance? The second step is to incorporate new information. And this new information, when we have scenarios in which we have high degrees of ignorance, we can call them insights. So insights are beliefs that might be related to knowledge, but are informed through unclear, opaque, or unrigorous process, which we also, in a sense, relate to, but are related to. But despite this, it seems to be that people have a strong attitudes toward them, and that they are informative and robust enough to guide our adoption or rejection of other beliefs. Insights allow us to evaluate some epistemic virtues of specific sets of beliefs, considering the ways in which other beliefs relate to them. Now, understanding, before relating insights to understanding, consists of building networks that successfully connect our scientific beliefs about the world. One of the challenges when we had ignorance of theoretical structure for achieving understanding is that we wouldn't be able to determine this type of connections. And so if the information contained by the insights is put together with independent theoretical knowledge, it becomes possible for scientists to generate a representation of an object, a possible word, or a proper part of one of the that represents how the object is embedded in a relevant theoretical domain. However, given the distinct sources of knowledge in these cases, and the lack of unity in methods that we might have and conceptual resources, scientists cannot often be sure that these possible words are actual, meaning that we are only getting possibility spaces. And that representations call some actual empirical domain. This is what is often called modal understanding. About modal understanding is that the main idea is that when we don't understand something in this sense, in the cases of defective theories or defective information in general, meaning incompleteness and inconsistency, what is happening, broadly speaking, is that some structure is being posited of some objects in some domain for the purposes of saying explanatory things about them, given a positive structure. And what we are going to be able to do is to navigate such a structure without necessarily being able to determine whether it is true or not about the world. It's like when we have a chess board already started in the game, and then we can determine which are the moves that are going to be more optimal for a winning strategy. But that wouldn't necessarily mean that those are going to be neither the crucial moves for achieving success, nor the only ones, nor that are going to be accurate descriptions of what is going to happen in the rest part of the game. And so that said, in the cases in which we have a lot of ignorance, and even if we can tolerate the defects, the ignorance that causes incompleteness or inconsistency, and we can still find strategies to reason within that in a safe way, we can still get insights from other ignorant bodies of beliefs and combine them with the theoretical structure that we have already grasped in order to gain this type of modal understanding. In general, what we have been saying here is that anomalies and ignorance of anomalies of any of these two types, either gaps or contradictions, are strictly and strongly related to ignorance of theoretical structure, especially when they are clearly resilient over time. And also, what we have said is that the identification of inferential patterns allow us to determine the reliability of how we are handling the defective information, the information that we ignore or the information that we consider to be inconsistent, but also they are going to allow us to transition from having the scenarios in which we have still recognizing ignorance of theoretical structure to move forward to having a type of scientific understanding, which is only going to be modal understanding. And that's it. Thank you.